Now we're going to figure out how to choose the best model. To get started, open up RStudio and import and attach the college dataset. In the prior video on regression, we built this model where we were predicting post-graduation earnings of business students based on the cost of attendance, graduation rate, percentage of students with debt, and whether or not the college or university was in a city. But is this the only model that could help us explain post-graduation earnings? Is it the best? Well, we don't know. And it's important to consider your options. So there are a few different models we could try. We could just evaluate earnings based on cost of attendance, or maybe cost, graduation rate, and percentage of students with debt. Or we can look at all four of these variables. So let's go ahead and build these models in R. So here we are in RStudio, and let's build a few models. First, we're going to build model 1. But before we do this, we want to attach the data set. This means we can just refer to the names of the variables without first having to use the name of the data set. So now let's build model 1. I'm going to do a linear regression model. Our dependent variable is earnings. And for our first model, we'll just do one independent variable, and it will be cost. So we see under global environment that model 1 has been created. Now let's try model 2. Also a linear model. Earnings is also our dependent variable. And now cost and graduation rate are going to be our independent variables. And now model 2 has been created, and we can see it in our global environment. And finally, let's look at model 3. Also a linear model. Earnings is our dependent variable. And here we're going to look at cost, graduation rate, percentage of students graduating with debt, and we'll look whether or not it's in a city. So now we've created these 3 models. Let's take a look at what model 1 looks like. So here we can see our coefficients and information on our R-squared and adjusted R-squared, our F statistics with the corresponding p-value. One thing that I think makes it a lot easier is if we don't use scientific notation in some circumstances. So looking at the values produced in this model output, especially here with our coefficients, I think that we might be able to more easily interpret this if we nix the scientific notation. So I'm going to use options, SCIPEN, and 999. And now let's take a look at the summary of model 1. That's much easier to read, at least in my opinion. So this is fine to look at an individual model, but I think it might be easier if we could look at the results of our models side by side. And one way we can do this is using the Stargazer package. So we're going to install packages, and Stargazer is the name of the package. All right, so now I'm going to add it to my working library. And now we're going to use the function Stargazer, and we are going to list the name of each of the models. So model 1, model 2, model 3, and then Stargazer can produce output in multiple formats, but in this case we just want text. So type is going to be text. So here we have our output of all three models side by side. We have our dependent variable is earnings, and then each of the independent variables is listed on the left-hand column. If that independent variable was not included in the model, there's just nothing there. So in our first model, we looked at cost only, and then the constant refers to the intercept. But we did not have the graduation rate, debt, or city variables in our first model. But we did have the graduation rate in our second model, and then we had all of these independent variables in our third model. And here we can compare them all side by side. And we can look at the coefficients for each of the variables. We also see that we have information on the observations, R squared, adjusted R squared, the standard error, as well as the F statistic. And these are just some of the ways that we can evaluate a model for its fitness. So as I said, there are several goodness of fit measures that summarize how well the sample regression equation fits the data. The first is the standard error of the estimate. We like this value to be smaller. The smaller the standard error, the tighter and more compact the data and the model are. We also have R squared, or the coefficient of determination. We like to use this in simple linear regression models, and generally bigger is better. The larger the value, the more of the variation in our dependent variable is explained by our independent variables. However, adjusted R squared is the preferred measure when we're working with multiple linear regression models because it takes into account the additional independent variables in the model. The equation for regular R squared will always produce a larger value as more independent variables are added to a model, even if those independent variables are completely irrelevant. So it's really important to use the adjusted R squared in scenarios where we have multiple independent variables because it takes into account those additional independent variables without just inflating the value just because. So let's talk a little bit about the standard error of the estimate. The calculation isn't terribly complicated. SSE is the error or residual sum of squares, K is our number of predictors, and N is our sample size. A regression equation has a great fit when the dispersion of the residuals is relatively small. And it's also important to note that the standard error of the estimate has the same units of measurement as the response. And for a given sample size, increasing the number of predictors reduces the numerator and denominator. So this overall effect enables us to determine if the added predictor variables improve the fit. When we're comparing models with the same response, the model with the smaller standard error of the estimate is preferred. R squared is our coefficient of determination, and it is the proportion of the sample variation in the response, or y variable, that is explained by the regression equation, or our x variables. It uses ANOVA in the context of regression. So the total variation in y is the total sum of squares. And we break that into two parts, the explained variation and unexplained variation. The variation in y explained by the sample regression equation is the regression sum of squares. So our value for the coefficient of determination, or r squared, is going to fall between 0 and 1, and the closer to 1, the better the fit. And here we just can illustrate the coefficient of determination and the components of it, where we're looking at the unexplained difference, the distance from A to B, and the explained difference from B to C, as well as the total difference between the mean and the observed value. But we also can't use r squared, or the coefficient of determination, for model comparison when the models do not include the same number of predictor or x variables. The coefficient of determination, as I said earlier, never decreases as we add more variables. And it may yield a really great value even as we add variables with no economic or intuitive foundation. The adjusted r squared, or the adjusted coefficient of determination, explicitly accounts for the sample size n and number of predictor variables k. So it imposes a penalty for additional predictors, but like with the regular coefficient of determination, the higher the adjusted r squared value, the better the model. So based on what we've gathered, we have models 1, 2, and 3, and we have their standard error of the estimate, coefficient of determination, and r squared. And take a second to look at these values, and why don't you pick the best model?